Welcome to the Explainer. Okay, let's just jump right into this. Imagine you've just been tasked with building a database for a massive, bustling university. You've got thousands of students, hundreds of instructors, courses, departments, schedules, the whole shebang. If you just throw all that data into a giant pile, you are going to get absolute chaos. To solve that, we use an entity relationship model, or ER model, to act as our master blueprint. And today, we're mastering a absolutely crucial part of that blueprint. We're looking at the properties that actually define our data, focusing specifically on attributes. By the end of this explainer, you'll know exactly how to take all that chaos and structure it into a perfectly organized university database.
Here's our quick syllabus for today. 1. Decoding ER model attributes. 2. Simple and composite attributes. 3. Single versus multi-valued attributes. 4. Calculating derived attributes. And wrapping up with 5. The complete university diagram. All right, let's kick things off with Section 1, Decoding ER model attributes. So in an ER model, an entity is just an object that exists in the real world, like a student. But an entity by itself, it's really just an empty shell. An attribute is the property or characteristic that actually describes that entity. It directly answers the question, what information do we actually need to store about this specific object? Because without attributes, knowing we have a student entity is completely useless. We wouldn't know their name, their major, or even how to contact them. To really see why this matters, just look at this totally messy student file. We've got an ID number, a full name, a couple of phone numbers, a date, an age, some emails, all just jumbled together in a list. If a computer system tries to search this for, say, everyone born in 2005, or tries to send an automated text to a primary phone number, it's going to crash and burn. This flat, chaotic list visually proves exactly why we need strict classification. We have to organize this data into specific attribute types. Moving right along to Section 2, Simple and Composite Attributes. Okay, so it really comes down to the atomic structure of your data. A simple attribute, which is often called an atomic attribute, stands entirely on its own. It cannot be divided into smaller, meaningful parts. But on the flip side, a composite attribute is complex. It contains a whole hierarchy of details and can absolutely be broken down into smaller, meaningful subparts that your database might actually need to access individually. Let's ground this with our student entity. Check out these simple attributes: gender, male or female, a student's GPA, or their unique student number. You cannot meaningfully split that student number into smaller database components. I mean, sure, it has letters and numbers, but breaking E22 away from the rest of the ID, that doesn't give us a standalone piece of data that the university can actually use. It is one atomic simple attribute. Now contrast that with a composite attribute, like an address. If we just shoved an entire address into one long line of text, analyzing our data would be a total nightmare. Think about it. What if the university wants to send a mass email to all students living in a specific county? By subdividing that composite attribute into smaller component attributes, like house number, street, town, county, and postal code, we make our modeling so much cleaner and our database infinitely more powerful. And here's how we actually visualize this in an ER diagram. You can see the main entity here, and connected right to it are composite attributes like name and address. Notice how name branches out even further into component attributes: first name, middle initial, and last name. Address branches into street, city, state, and zip code. And look, street even branches down further than that. This tree-like hierarchy is brilliant because it visually communicates to any database developer exactly how the data needs to be structured under the hood. All right, Section 3, Single versus Multi-Valued Attributes. Now we're looking at strict rules versus flexibility. This is the difference between single-valued and multi-valued attributes. A single-valued attribute is definitive. It stores strictly one value for each entity occurrence, no exceptions. But a multi-valued attribute, that's expansive and flexible. It can store 0, 1, or a whole set of values for a single entity occurrence. Take a look at these single-valued examples for our students. An individual student will only ever possess one date of birth. They'll only have one unique admission number assigned to them. At any given time, they're enrolled under one primary degree program, and they have one gender marker in the system. There is literally no scenario where a student has 3 different dates of birth, right? It is strictly single-valued. But hey, a student's life isn't always that simple, which is exactly why we need multi-valued attributes. A single student can easily have multiple phone numbers, maybe a mobile and a home landline. They almost certainly have multiple email addresses, a personal one and an official university one.
If we're tracking languages spoken or programming skills, one student might know Java, Python, and SQL. If we try to force these into a single valued box, we are quite literally losing valuable data.
So, to handle this on paper, the industry uses a really clear visual signpost. When you draw your ER diagram, you flag multi-valued attributes by enclosing them in a double oval. Or, if you're writing out a text schema, you just put the attribute name in braces, like with phone numbers here. This is a vital signal that tells the database engineers, hey, you need to set up a special table just to handle all these multiple values.
Next up, Section 4, Calculating Derived Attributes.
Okay, I want you to really think about this for a second. It's a critical design question. How do we store a student's age when it literally changes every single year? Because if I type 21 into the database today, next year that data is completely wrong. If you permanently store dynamic data like that, your database is going to quickly turn into a museum of outdated, inaccurate information.
And the secret here, it's the derived attribute. This is an attribute whose value isn't permanently stored in the database at all. Instead, it's computed or calculated on the fly from another related base attribute exactly when the user requests it. Honestly, this is a total game changer for database accuracy. Here's the classic example to show you how this works. The base attribute, the one we actually do save in the database permanently, is the date of birth. That is set in stone. It never changes. The derived attribute is age. So, when a university administrator opens a student's file and wants to see how old they are, the database quickly takes today's date, subtracts the date of birth, and spits out the age. It calculates it every single time it's asked, which means it is always 100% accurate. To show this neat little trick in your blueprint, you just use another visual signpost. Derived attributes get represented by a dashed oval in the ER diagram. When a developer sees that dashed line, they know instantly, okay, don't build a storage space for this. I need to write a formula to calculate it instead. And finally, Section 5, the complete university diagram.
Let's put it all together. Here is your ultimate master cheat sheet. These are the 5 focal attribute types we've used to organize that messy student data into a flawless, functioning structure. We have simple attributes, like a student number that you just can't break down, composite attributes, like an address, that neatly branch into a hierarchy, single-valued attributes, like date of birth, that lock an entity to one strict value, multi-valued attributes, like phone numbers, that give us flexibility for a bunch of values, and, of course, derived attributes, like age, which cleverly calculate data on the fly. This table right here, this is your foundational key to translating real-world chaos into a highly logical database schema.
So, you've completely nailed attributes. Your entities are rich with well-organized, optimized data. But you know what? A bunch of isolated student entities doesn't make a university. A university is students taking courses, taught by instructors, housed in specific departments. So, with your entities and attributes perfectly structured, the next great question is, what relationships are you going to build to connect it all together? That is the next exciting phase of database design. Thank you so much for joining me on this explainer, and keep building.